Welcome back, everybody. We're going to finish section 2.1, just looking at a couple of word problems. Linear functions have a lot of applications, so we're going to take a look at just a few. There's no way I can give you every situation that you'll come across, but I can give you a couple of situations you might come across to give you a little bit of experience, and then hopefully that experience will carry you if you get a word problem that you haven't necessarily seen before. All right, I will tell you that these problems come from Active Prelude to Calculus, which is our book B, and they're in section 1.4, linear functions. All right, so the first one, pretty straightforward. The town's population initially has 28,750 people, and then grows at a constant rate of 825 people per year. Find the linear model for the number of people in the town in year T. So the number of years basically grows the model. So first we got to start by labeling certain things. Our town starts at 28,750 people. And if we were looking at a linear model, right, in year 0, we would be at 28,750. So I'm going to call that the y-intercept. Now, they say the town grows at a constant rate of 825. All right, if it grows at a rate of 825, that must be the rate of change. And as we noted, the rate of change is the slope. All right, so our f of t, right, because f is what's in the problem, is going to be 825 times the number of years since we started counting, plus 28,750. All right, so we can double check our work quickly by saying in year 0, we have 28,750, which is what we initially should have. And in year 1, we grow by 825. In year 2, we grow by 825 times 2. So pretty straightforward, pretty quick. It's just a matter of picking the different elements out of the problem and assigning them to either the slope, the y-intercept. Okay. Next one is a little different. All right. A different town's population Q is given by G of t equals 42,505 minus 465t. I'm going to rewrite that down here. Just because it went over to 2 lines. What is the slope of this function and what does it mean in the model? All right. So we've got to figure out what our rate of change is and what is staying constant. Well, even though this is out of order technically, my rate of change is right here, the 465, because in year 0, we have 42,505. In year 1, we're subtracting 465. In year 2, we're subtracting 465 times 2. All right, so my slope equals negative 465. And they say, write a sentence to explain what the negative 465 means. So this is something that I do from time to time, is I will make you write a sentence to explain what the math means. In this case, what it means is the town's population is decreasing at a rate of 465 people per year. So that's the sentence you would write. Is decreasing at a rate of 465 people per year. All right, and population growth or population decrease is a good application of these types of models, very often done. For example, a population's town could decrease because of lack of jobs, because of crime, food shortages. They could migrate to another town where there's either more jobs, more food, more economic stability. All right. The last one's kind of a big one. All right. It's activity 1.4.3. And again, this is out of Active Prelude to Calculus. The summit of Africa's largest peak, Mount Kilimanjaro, has two main ice fields and a glacier at its peak. Geologists measured the ice cover in the year 2000 to be, right? And very often we do this, is that if we're starting in the year 2000, we'll call that t equals 0. And we do that to simplify our process, all right? If you wanted to make a graph out of this, right, you would rather start at 0 than start at 2000 over on the x-axis to be approximately 1,951 meters squared in the year 2007. All right, so in t equals 0, we have 1,951 meters squared. In the year 2007, we have 1,555 meters squared. All right, so then there's 5 parts, and we'll go through each one of these parts separately in an effort to keep this well organized. All right, so there we go. Suppose that the amount of ice cover at the peak of Mount Kilimanjaro is changing at a constant average rate from year to year. And that's key. With a linear model, the slope is always a constant average rate of change. All right, so we're looking for a linear model whose output is the area A in square meters in the year t. So again, t is going to be our change. So if we're looking for a linear model, we're going to start with our slope. All right, and in year 0, how much ice cover do we have? We have 1,951. And if 2007 would be year 7, we have 1,555. All right, so let's put this into the slope formula. Now, my expectation is my slope should be negative. And the reason that's my expectation is because my ice cover is diminishing. It's decreasing. Anytime you have a decrease, and you're using a linear model, you should have an expectation that your slope is going to be negative. All right? And that won't necessarily tell you if you're right or wrong, but if you wind up with a positive slope for some reason, and your expectation was a negative slope, I would just quickly double check your work. All right, so I have 1555 minus 1951 over 7 minus 0. And when I do the subtraction, I got negative 396 over 7. And that is indeed my slope. All right, so now I'm going to use my point slope form because I have a point and I have my slope. So I'm going to say, and I used this point just because I think the 0 is going to be easier to calculate. Y minus 1951 equals negative 396 over 7 times x minus 0. All right, so now I'm going to do my algebra. And I get y minus 1951 equals negative 396 divided by 7x. And then I'm going to add 1951 to both sides, and I get y equals negative 396 divided by 7x plus 1951. All right. And what that means to me is that the ice is decaying. Let's see, what is number 2? What do the slope and the intercept mean you found in A? In particular, what are the units on slope? All right. So the second part just feeds off the first one. So my negative 396 divided by 7. What are the units on that? And the units are meters squared, because that's how much ice is decreasing, right? We have area of ice decreasing. So it's 300 meters squared. And what it means is the ice is melting at a rate of negative 396 divided by 7 each year, all right, starting in the year 2000. All right. Yeah, at this rate. So let's take a look at number 3. Scroll up. Number 3 says compute f of 17. What does this quantity measure? Write a complete sentence to explain. All right. So if we want f of 17, negative 396 divided by 7 times 17 plus 1951. So why don't you at this point pause the video, do some of these calculations. You may need a calculator just to finish it off, get a decimal approximation. But let's talk about the answer on the back end. Okay, so hopefully you did the work. I rounded to the tenths. I got 989.3, and that's in meters squared, and that is the ice cover in the year 2017. I'll tell you, for my taste, I need labels. If I'm giving you a word problem, I'd like to see a label. I'm sure other teachers would like to see a label. So please make sure that you write out the whole thing, meters squared, and then is the ice cover, especially since I asked you what that number means. All right. So let's take a look at the next one. If this model holds further in the future, when do we predict the ice cover will vanish? All right. Well, if the ice cover is going to vanish, that means our equation, negative 396 divided by 7x plus 1951, is going to equal 0 at some point. And the only question is, when? And x will give us the number of years since the year 2000. So here's what I'd like you to do. This is an algebra problem, and you guys should be able to do your algebra. So why don't you work this down and see what x equals, and we'll talk about the answer on the back end. Okay, so if you added, or you subtracted 1951, I get negative 396 divided by 7x equals negative 1951. And then you multiplied it times 7. You get negative 396x equals 13,657. Sorry, let me make that better. And then that should be a negative. And then we're going to divide both sides by negative 396. So I get x equals negative 13,657 divided by negative 396. All right. Now that is approximately 34.487 years. All right. We don't really talk about 487 years, so we can say 34.5. So by June of 2034, the ice will be gone. All right. So then the last piece Says, in light of your work above, what's a reasonable domain and what is the corresponding range? All right, so now here's the thing. Technically, this is a polynomial. So the domain can go from negative infinity to positive infinity, but we have a context, right? Our context is the ice melting, right? So the last piece, right, is basically we need a domain, right? So we are starting at year 0. We're starting at 2000. We don't know what happened in 1999, and we can't use it, all right? So we're starting at year 0, and then we end in June of 2034, maybe a little bit before, but June of 2030 is a reasonable domain. So 34.5 is reasonable. It's a little more than we need, but all the question asked was reasonable. All right, now the range. Now the range, remember, was our ice. And our ice, we can't get any lower than 0. Once the ice is gone, it's gone, right? So we're starting at 0. And how big can the ice get? Well, the biggest the ice ever was in year 0, the year 2000, which was 1951. All right, so that's basically it. And what this particular problem does is it really helps you understand how to take it from a context and bring it into the math, all right? So we're bringing it from Mount Kilimanjaro to domain and range and slope and things like that. So we want to see how one relates to the other. Guys, this was a short one. Thanks for listening. There's going to be a lot more practice before it's all done, but I'll see you next time. Thanks. Bye.